number 17, we're again testing a p-value here. So we have the series from n equals 2 to infinity of 1 over n times ln n to the p. And we want to know for which values of p does this converge. So this is a great form for using the integral test. And the reason being, we have a function ln n and its derivative 1 over n right within the function. So we know we're going to be able to use substitution. It's going to work out nice. So remember, if for a series to converge, if you're going to use the integral test, we have 2 to x. Actually, let me go with 2 to t. Limit as t goes to infinity. We're going to use 1 over x times ln of x to the p. So if we want this series to converge, this improper integral has to give you a definite value. It can't give you any sort of infinite answer or dne. So this can be easily solved with u being ln x. Therefore, we get du equals 1 over x dx, and you can see, oops, didn't write the dx there. 1 over x dx is in our integral. So we're going from 2 to t, limit t goes to infinity. In terms of u now, this just becomes 1 over u to the p du. So now we need to think about our antiderivatives and what they're going to give us. So we need to know which values of p does it converge. If you notice, all the answer choices are p is greater than something. So let's just try a couple of things here and see what happens. Well, if p is 0, let's try that one first because that's the easiest one. Then this integral is just u, because this would be 1 du. And if the integral is u, we have ln x, but ln x as t goes to infinity definitely gives us infinity. So we have an infinite answer with p equals 0. So p equals 0 would definitely not work. So let's try with p equals 1. If p equals 1, then we just have 1 over u. The antiderivative of 1 over u is ln u. So we have ln u. U is ln x, so this is ln of ln x from 2 to t, limit as t goes to infinity. We run into the same problem though, because as t goes to infinity, ln of infinity as you go towards infinity becomes infinity, and then this ln as that goes towards infinity is going to be infinity. So we're still ending up with infinity, so p equals 1 does not work either. So the question becomes will anything bigger than 1 work, or do we have to go all the way to 2? And that is something you can answer just by thinking about your anti-differentiation rules. So if you have some power on this that's not 1, what happens to it? So if you use your anti-derivative rules, you add 1 to the power and all that stuff there. So you can see that even if this was 1 over u to the 1.1 power, what would you do? This is like u to the negative 1.1. You would add 1, we'd still have some negative power left. So as long as this p is anything greater than 1, when you add 1 to the power, you still have some negative power left. So you're going to still end up with u on the denominator. In this case, it would be to the 0.1 power. And then divided by that new power, so we'd have 10 up here, like that. But no matter how small that this remainder power is, when we do the limit as t goes to infinity, you have infinity on the bottom, that kills it, it goes to 0. We definitely get a finite answer. So we need p to be greater than 1. So that last explanation I did there is just how you could differentiate between greater than 1 or greater than or equal to 2. So as soon as p passes 1, that's when you still get terms left on the denominator. When p equals 1, you still get ln, and ln is still infinite, which doesn't suffice here.